Hi, this is Maggie from Design Code Debug Repeat. Welcome to the channel. This is video 12 in the Adventures with Python series, in which we learn Python by building a text adventure game. No prior programming experience is needed, but you should watch the series videos in order. I'll link the playlist here and in the description. Let's get started. In the last 3 videos, we've built some classes that work with our game. In doing so, we've learned how to define a class and how to define an enumerated type, how to instantiate objects of the class, or how to write and invoke class-level methods if the class is not meant to be instantiated, and different ways that classes can relate to each other. They can have a composition relationship, as with the inventory and location, and they can have a navigation relationship, as with the locations with each other. We've seen firsthand how a class with a well-designed public interface and private implementation can be changed without impacting the rest of the system. In this video, we're going to design the entire game as an object-oriented system. And as you can see, this isn't necessary for a functional system. You can mix objects into a system that isn't an object-oriented design. But a system composed of objects with clearly specified data and responsibilities will be easier to extend and maintain. I'd much rather modify one or more well-encapsulated objects with clear responsibilities and interactions than have to work with data and logic distributed throughout a monolithic system. Now, we have already created inventory, location, and command objects, and I've suggested to you that you try designing an item class. Why did I create those classes? Where do you get ideas for classes when you're designing an object-oriented system? Let's go through a process. This method that I follow is a simplification of Ivar Jakobsson's method described in his book Object-Oriented Software Engineering, which I'll link in the description. Jakobsson has written much more recent books, but this is the book I have and the process I have used. I think of Jakobsson as one of the founding parents of UML. You can also read descriptions of the elements that were adopted from Jakobsson into UML in the Unified Modeling Language User Guide, authored by Grady Booch, James Rumbaugh, and Jakobsson. I will also link that book in the description. What I do is start with a description of the system and as complete a set of use cases as I can create. A use case is a transaction between a user role, called an actor, and your system. The transaction begins with an actor's action and ends when the system is awaiting another action. To create use cases, begin by defining user roles. Will your system users always have one role when using your system, or might they have several different roles? You're going to write the use cases for each role. In our system, our user is always going to be in the player role. Our user is always playing our game. They're never going to write scripts for it, for example, or design a dungeon with it. Our game is strictly built by us and played by the user. But if you want, write a game that has an API that allows the user to script it, or write a game that has a dungeon building mode. If you do, you'll want to write use cases for those activities in addition to playing the game. So if you do, you might have scripter, builder, and player actors. For our game, with our one-player role, the use cases are very straightforward. They correspond to the commands the player can type. We're cheating in a way because we already have a working game, so we already know what the game we're designing can do. So my use cases are start the game, load a game, save the game, exit a location, look at the current location, list player inventory, take an item, drop an item, examine an item, quit. That's all they can do. This diagram is called a use case diagram. It's a UML diagram, and you can see it's just showing my player role and basically lists the use cases. If you have more actors, you can draw lines from the actors to the use cases those actors can enact, or what functionality each actor is expecting the system to provide. If you want to add more functionality, you write a new use case. For example, I might like to write use an item and talk to a character. Our game doesn't even have usable items or characters yet, but this gives us a sense of what kind of functionality we might like to design for and how we begin designing for it. We'll look at a use case in detail in a moment, but before we do, you will also want to identify object candidates. One way to do this is to identify nouns in a description of the system. I have a brief description of our system here, and if we pull out the nouns, we get project, game, player, location, item, state, command, direction, position, exit, description, title, narrative, inventory, word, phrase, action, feedback. Once you've identified some candidate objects, try attaching data and responsibilities to them. Even if you think you want to throw some away, don't do it yet. You can also layer on top of that any knowledge you have of design patterns or even your general programming experience, because our system may need some objects that do structural work but don't necessarily map to a noun in the system description. For example, we might want an object to manage loading and saving. Or we might want to give objects roles on top of their current roles, such as a subject and observer role, so that one object can stay synchronized with another. For each use case, we should write out the sequence of events that are part of the use case. For player lists their inventory, I have written, the player types inventory at the command prompt. If there are any items in the player's inventory, the system displays you have, followed by a list of inventory item names. If there are not any items in the player's inventory, the system displays you aren't carrying anything. That's a complete use case because it begins with a player action and ends when the action is complete and the system is waiting for another player action. For more complicated use cases, you can write out the average case scenario that follows the most common execution path, and either write separate use cases for situations where the use case takes alternate paths, or extend the use case with a short description of the alternate path. The actor's use cases, a human-computer interface description, and object candidates together form a requirements model of our game. I'm considering that because we already have a working prototype of our game, that the game we have specifies the human-computer interface. This requirements model is a simplification of Jakobson's method, which is meant for complex, large-scale systems. There is more work that can be done on all of these pieces, but we'll use our existing program to fill in any gaps. Our next step is developing an analysis model in which we figure out which objects in the system will interact to fulfill each use case and how. Now is the time we start giving our objects responsibilities and mapping out how they interact to implement the system specifications. So we will take our use cases and generate sequence diagrams from them. We'll create a sequence diagram for the player lists their inventory use case. You know what our current system does if the player types inventory. It asks the command if the command type is command type.inventory. Then it asks the player inventory if it's empty, and if it isn't, it prints the inventory, which invokes the str method behind the scenes. But I'm redesigning this system now as an object-oriented system, so my use case may not exactly follow the code we've already written. The software I'm using for this is called draw.io. I suggest it to my students for drawing UML diagrams. It's free and pretty easy to use. I'll include a link in the description. To start, I create a new diagram, and from the basic category on the left, I choose sequence diagram in the center, and I can give it a name. I'll call it SD for sequence diagram, player lists their inventory. And I'm given this starter diagram. I'm going to delete a few components from the starter diagram and then use it to explain what a sequence diagram is. A sequence diagram will show how objects interact by sending messages to each other to fulfill a use case. At the top of the diagram are the objects. They are represented as a box with the name, usually object name : class name, and then a lifeline extends from the box to the bottom of the diagram. The lifeline is a vertical dashed line. That lifeline represents the existence of the object during the use case, but it also represents time. The top of the diagram is the start of the use case, and the bottom is the end. Messages are solid arrows to and mostly between lifelines. We read the diagram top to bottom, indicating the order in which messages are sent. The execution in the diagram starts at this message on the left, labeled dispatch. It points to the first object's lifeline, and there is then a box over the lifeline called an activation bar. The activation bar represents that the first object has control. Think of it as the period during which that method is executing, or on the call stack waiting for another method to return. The activation bar extends from the start of a method execution to the end. We can see that within that bar, the object sends a dispatch message to the second object, and the second object then has an activation bar on its lifeline for where it's responding to the first object's message. That's when the second object has control and its method is executing. At the bottom of the second object's activation bar is a dashed line that says return, showing that the method completed execution and control is returned to the first object. You do not have to show returns. They are implicit when the activation bar ends. I only show them in my diagrams when a value is being returned, or if for some other reason I feel showing the return makes the diagram clearer. Okay, so let's replace this with our use case. First, I'm going to rename the first object as game of class game. We don't have a game class yet, but I imagine a game object as being responsible for executing the game loop and managing the interaction with the player. And that first arrow marked dispatch, I will rename to quote inventory unquote. So that means we'll have a game class. It's responding to the player typing inventory. If I go down to the UML symbols, I can find an actor symbol. I'll drag that out to the left and name it player. The player types inventory. The player starts this use case. Now I'm going to show the interaction with the command object. So I'm going to rename the second object command of class command. And we would ask the command object a lot of questions, actually. We're going to ask until we get back the correct type of command. But I'm going to show here that we ask is type inventory and it sends back true. So I will have a small activation bar for this method and a dashed line at the bottom, and I'll put true on that line. The game will then ask the inventory if it's empty. So we'll make another lifeline on this diagram called player inventory of class inventory. Technically, I believe game and player inventory should be underlined, but I don't want to get into too much nitpicking in this diagram. If you want to nitpick, I'm happy to discuss sequence diagrams with you in the comments. Drop any questions you have below. What is important about diagrams is that they communicate clearly and consistently about your design. If you don't know the proper way to show something and your resources and the folks you're working with don't have an answer, add a note. Now I'll send the message is empty to player inventory, and it will send back, so a dashed line back, empty. That could be true or false. Then let's assume for the moment that it's false. I'm going to ask it to give me a string version of itself suitable for displaying to the player. So I'll send it a message called toString. Now, I'm going to design the system with item objects, even though I haven't created that class before in our videos. Maybe you did after the last video. But if the inventory has a dictionary or list of item objects, it should get the names from the item objects. So I'm going to put another lifeline here, and for this I'm just going to put :item as the name. These are just whatever item objects happen to be in the player inventory. And I'll have the inventory send the item object the getName message, and the item will return its name. And then the inventory can return an inventory string, so on a dashed line back to the game. So you can see the order in which messages are sent and which objects send which messages to other objects in which methods. In response to an inventory command typed by the player, the game sends isType inventory message to command and receives true back. It then sends the isEmpty message to the player inventory. It then sends the toString message to the player inventory, and in response to that message, the player inventory sends the getName message to its items. The items send back their names, and the inventory sends back its list of item names. What I haven't captured here yet is, first, the looping. There could be many items in the inventory. To show a loop in a sequence diagram, we put a frame around the messages that are part of the loop. You can find a frame in the UML section below. It's basically a rectangle that surrounds the messages. It has a little tag in the upper left. For a loop, we put the word loop in that tag. So that goes around just the getName message being sent from the player inventory to the items. We also put a guard under a little tag that explains when we're looping. A guard is a little text in square brackets. I'll put all items. We're looping over all items. The other thing we haven't captured is the conditional nature of sending the inventory the toString message. We'll only do that if the inventory isn't empty. So I'll put another frame around the toString message and resulting messages, and in that little tag I put alt, and I'll add a guard under the tag that says not empty. We only send a toString if that boolean came back false. So that's pretty complete, and it includes a loop and a conditional block, so there's a lot in this little diagram, but not too many messages, which hopefully makes it easy to follow. I don't know that the loop and the conditional block are entirely necessary. They don't help us determine which messages are sent in response to an inventory command, and they don't help us determine which methods we need to write for each class. But they do help us write an algorithm for the game method that will respond to an inventory command. and they do help us understand how it works. What we would do to design the entire system is draw all of the sequence diagrams, and then look at the classes at the top of each diagram and what messages each class is responding to, and collect those up into class diagrams. And then we might want to look the whole system over and decide if each object is coherent, or if we need to change the way the responsibilities are distributed. And we also need to decide how each object is connected to the objects it sends messages to. Do they have a composition relationship? I would say the inventory and item classes have a composition relationship, but the items don't live exclusively with one inventory. They can move between them. The game and the player inventory also have a composition relationship. The player inventory is created at the start of the game and exists through the end. Command objects are temporary objects. They might exist only while the play method of the game is executing. These are not necessarily easy decisions to make. Sequence diagrams are helpful answering these questions because they help you think through how each interaction will be fulfilled by the objects in your system. Now, I have drawn the majority of the sequence diagrams for this game by hand because that's much quicker for me, but I'll drop a few in my GitHub repository along with the code so you can see a few more examples. I'm going to include them in an HTML format. Feel free to ask questions about them in the comments and I'll answer them as best I can. But let's move on to the code. I'm sure you're curious to see this implemented as a fully object-oriented system. The classes I decided to include are game, loader, location, inventory, item, and command, along with the command type enumerated type. Let's start with the main program. It has basically been split into the game class and the loader class. This is shabby-appy v12.py, and at the bottom, you can see the main function creates a game object and sends it the play message. On the right, you can see the class diagram for the game object. It has only those two public methods, init and play. It has a lot of private helper methods, and the variables that make up a dungeon are all fields now of the game class, the player inventory, the data that we read from and write to, the JSON, which includes all of the locations, I've called that save data, the reference to the current location, and I have an additional reference to the loader. The init method creates the loader, loads the save data in by sending the loader the load Abby message, and then pulls out the pieces the game needs into separate variables, the current location and player inventory. This isn't strictly necessary and never was, but it'll make the code easier to read. And then let's jump down to play. We get a command from the user, instantiate a command object with it, and then I have the same if, elif block that I had before. I've just extracted the code from each block and put it in a helper method, such as handle move or handle restore, that returns either a string or none. So each helper method takes either the command or no additional parameters beyond self, handles the command, then returns whatever messages we need to let the player know how that went. At the bottom of the loop, after handling the player's command, if there was a message, we print it, and then set it back to none for the next time through the loop. So that code is mostly unchanged. It's just been distributed into methods that work with the fields of the object. So if we look at handle examine, for example, you can see it's working with self._player inventory, the player inventory that's a field of this game object. And instead of printing messages for the player, they're accumulated into a string that's returned. The loader is another new class, but it's also composed primarily of code we've already written. I decided to encapsulate all of the interactions with the file system in the loader class. You can imagine that if we want to add features such as letting the user choose a save or restore file from a file picker, we would only have to change code in the loader class and nowhere else. I've defined two class-level constants, start and save, so the game can tell the loadAbby method whether it's loading from the start state or the save state without passing in what that path is. This again encapsulates that file system information in the loader class, which has those paths, start path and save path, as its fields. Now I've hard-coded them into the initializer. And then saveAbby and loadAbby have barely changed. I just used the path fields rather than the parameters that we had in the last version of the game. The most annoying change I made to this game is adding an item class because it required changing the inventory class and the abby.json file. So it required changing the toJSON and fromJSON of the inventory class. It was annoying because I think the JSON reading and writing code is the least pleasant to write, because I had to completely rewrite most of the testing for the inventory since there were a lot of hard-coded inventory items, and since the item class doesn't do anything new. So it seems like a lot of cost for no benefit. But I do plan to create a version of this game in which the items can do something to the dungeon, otherwise it's pretty boring. To do that, I'm going to want an item class. So here's the upfront work I've done. I've changed the JSON so that an inventory is a dictionary of name serialized item pairs. A serialized item right now is name as a key, and then the name of the item as the value, and description as a key, and then the description of the item as a value. You can see I've left inventory mostly the same, but I'm no longer allowing an argument constructor. You can only read in an inventory from JSON after creating an empty inventory, or you could add items to an inventory. That feature, the argument constructor, was never used. I was only using it in testing. I changed the data type of the item parameter in add. In the inventory dictionary, I have an item object keyed on the item's name, so most of this code didn't have to change. In examine, I send the get description message to the item itself. And then I had to accumulate a JSON version of the inventory by sending the toJSON message to each item, so that was a little bit of work. The item class itself is very simple, a name and a description for fields, init, getName, getDescription, toJSON, and fromJSON methods. And the game works the same as before. So that may seem like a lot of work for something that's not very different, but from my perspective, it's got a clear structure now in which the different responsibilities of the system are encapsulated in objects. I can see, for the changes I want to make, which objects will need to be updated, and I know that very little of the rest of the system, if any at all, will be impacted. I hope to bring you at least one more video in this series in which I add behavior to items. At a minimum, we want to be able to unlock a door, right? But your imagination is the limit with what we can do with items. So in the next video, I'm going to show you the mechanism I've come up with for how to implement really impactful items in a general way. In other words, I don't want a bunch of special cases. I want a structure that allows us to unlock a door, or flood a room, or reveal hidden treasure. To practice, as always, I recommend you try rewriting what we've done here from scratch. Try drawing sequence diagrams for some of the use cases I didn't include on GitHub. But I also suggest that you come up with an object-oriented version of your monster game. Start by writing a description of the game and use cases. Then look for objects by looking for nouns in your description and start sketching out how those objects might interact to fulfill each use case. Then build those objects. It's not simple. I'm not trying to make it sound simple. But if you keep it small enough at first, it'll be great experience, and I think you'll be successful. When you're feeling confident with designing an object-oriented system, or at least maybe like it will be doable with practice, join me for the next installment of Adventures with Python. As always, have fun and keep coding.